So thanks for the introduction. Very, very nice, very kind. I think that you now can see my screen, right?
Yes, very well.
And for me, it's a real pleasure today and give my keynote. And I would like to thank Patrizia for inviting me. And this, I think, will be a very nice opportunity to even know better each other in terms of research and possible integration and future cooperation. Well, what I'm going to present today is this research that we are doing between Siena and Genova on the concept of wearable haptic that are highly wearable. So when I talk about wearable haptics here, I mean something that weighs like 100, 120 grams, no more. And how these interfaces that you wear on your body, on the human body, can improve the communication, the interaction between humans, and also between humans and machines, and in particular robot in this case. What I would like to highlight also is that, of course, this is not a work done by myself, but by a group. This is the research group. I have a research group of about 15, 20 people between Siena and Genova. And as you can see here, there are some shots of our research. And there always, there is always a hand. So on the right, there is a hand. On the left, there is always a hand. Actually, what we are doing in our research, we are really focused on the human, the robotic, and the virtual hand. So the hand like a sort of interface between the body and the environment. And of course, this can happen in the real reality with the human hands. This can happen between artificial piece of robots and environment, and this can occur, of course, also in the virtual reality and in augmented reality. So we are exactly in that area. If you want to highlight this from a mathematical point of view, so it's like we are becoming we are accumulating a lot of knowledge on the interaction, modeling, and simulation, and rendering and control. Because I'm talking about interaction by contact. So the kind of interface that we are dealing with are interfaces that deal with the body, the bodily interaction. So I need to push something, I need to feel some force from the environment. And so we are not focusing on audio or visual interfaces. Okay, of course, the haptics is so in particular in this talk, I will show how, I will briefly introduce our current research on highly wearable haptics. Then I will show a couple of applications of these highly wearable haptics, of course, in virtual reality, in guidance and human-human interaction, because yes, of course, you can use this tactile interaction, not only to interact with the environment, but also to be guided. Think to someone close to me that just tries to move me on the left, on the right. And also, in the last part of my keynote, I will show how these highly wearable haptic devices can be useful to interact to interact with machines, to augment the level of communication, of interfacing between machines and humans. Okay, so let's introduce the haptics. I think that you are familiar, and please stop me in case you want to know some details. But basically, when you touch an object like on the left, what you are doing is you're applying a force, and the object reacts with a force equal and opposite on your hand or on the tool that you are using to touch the body. When you want to go virtual, basically the object does not exist anymore, and you have a virtual sphere, in this case on the right, and this virtual sphere is generating a virtual force that becomes real thanks to the robot, because the robot is applying at the end tip of the pen a force that is equal exactly to the force that a real ball would apply on on the pen if it was there. So the robot is a device to render, to display forces that appear in virtual reality or augmented reality, of course. This is the story. I mean, the upper part is a commercial device from Sensible. And there are many devices. These are called the kinesthetic device. But as you can see, they do not capture. And this now it comes a little bit our research in my lab. So the picture on the top does not capture the real interaction with an object like a glass, like a notebook, whatever, your mobile phone, or simply an object that you want to touch in a museum. Because typically you interact with multiple finger and not with a pen. The upper part is very useful, for example, if you want to simulate surgery. If you want to go for virtual surgery applications, then the tool simulation, like that one that resembled the surgical tool, is very important to deal with. But in case you want to have a complete interaction with the environment, you need to go with all your fingers. Well, we did, this is, I mean, I'm presenting the research in my lab. You can see here, at the beginning, we wanted to go from a single contact point on the top to multiple contact point, but by using the classical approach that uses a robot for each finger. And you hear there was a robot for the index and a robot for the thumb. And you can imagine that was really, difficult to build application with this. Then we started to develop exoskeleton, like you can see on the lower part of this slide. And this is our last version of exoskeleton. Very interesting indeed. But is wearable. The upper part is not wearable. Indeed, it's called grounded haptics. The lower part is wearable, but it's not wearable at the level that we want to work with. In particular, we want to deal with highly wearables. When I say highly wearables, to give you a picture, I'm focusing more on the bands, on the rings, on the things that you have on your body when you go for jogging or when you go for any kind of application that you can use, for example, with your smart watch. So we want to go there. And how to do this? I mean, this is just a very simple but interesting, actually, on the left, you see a kinematic chain representing the robot applying forces on your body. Then the exoskeleton, you simply take this kinematic chain, you ground this kinematic chain, and you put your kinematic chain on the wrist, and you have the exoskeleton in the center. If you want to reduce the impact of the complexity of this device, what you have to do is to reduce the kinematic chain. So to remove all the links and the joints parts from the wrist to the end pit, and you end up to a design that is the one on the right. So you have to concentrate at your fingertips, okay? Assuming that you are interacting with your fingertips. So this is exactly where we entered in our research, and we developed a very small robot like this one that is not an exoskeleton anymore, but is something that you wear on your fingertips like a thimble and simply replicates the force that you can have at interaction with a virtual ball, like on the left. You see, in particular, the platform, the blue platform at your finger is moved by three motors on the top of the finger, and the platform orients itself according to the tangent plane of the surface, and is squeezing the finger the more you push on the robot. I think that now the concept is more clear, so I have concentrated all the mechanics as close as possible to the point of application of the force, and I've reduced the impact and the complexity of the mechanics around on the body that was of the exoskeleton before. Very good. This is exactly the jump that we did, as you can see here, right? So we were talking about, on the top of the slide, of an interaction with a robot that has a specific workspace. In particular, on the top, you cannot go around. You have to stay in the workspace of this machine. You cannot go in Piazza del Campo with this robot unless you put it on a desk on a coffee shop. On the bottom part, you see our robot that becomes wearable. Okay, so it's something that becomes something that you can bring on your body. And if you can see, if you make a parallel with the auditory modality, okay, so we are doing exactly the same jump, technological paradigm shift that occurred in audio when we went from classical speakers in our rooms to something that is wearable, like the headphones of the Sony Walkman. Sony Walkman in 1979 patented the idea of these headphones, and was really, I mean, most of the people remember the cassette, but actually the very important paradigm shift that they did in technology was to go from a closed environment like our houses in something that you can go around. So you can listen to the music or whatever by going around with a series of problems. Like, for example, all your music now should be portable. So there was a push in the digital transformation era, where all our LP, vinyl discs were transformed in digital digital data, and they were put on cassette and then on our disk, and now on our current SSD. And I would say that the Sony Walkman was probably one of the most powerful technological motivation to go digital for the sound. And of course, you know that everything now is happening with the headphones. So, and as you can see, if you are a little bit expert of audio, you see that from here, from the top to the bottom, you are missing something. Typically, what you miss is the bass. No, you know that with the headphones you listen a lot of medium and high frequency, but you are losing a lot the low frequency. And this is exactly what happens in our finger interface. In our finger interface, I want to go fast on this part, but typically we have the interaction at the tactile level, at the haptic level, that is kinesthetic, which means that we feel the environment thanks to our tendons and muscles. And also we have the interaction that is cutaneous. So we feel the environment thanks to our skin. So in some sense, it's like a parallel between bass and high frequency in the audio modality. And here we have the kinesthetic that is done by the robot because it is interacting with your muscle, and the cutaneous that is the most important one that we are facing with wearables. Okay, so with these wearables in particular, we are interfering, we are stimulating the cutaneous channel, okay, and not the muscles. And the cutaneous channel in this is very important. This is an old experiment by Johansson, a very famous neuroscientist from Sweden, and this showed this is an healthy subject who has been anesthetized at the cutaneous level, at the fingers, so she's not able to feel anything with their skin, and the task was to move the objects from this box to outside. She's healthy, just anesthetized. So without the skin, she's not able to move the objects out of the box. What this means? This means that the cutaneous part is bringing to our body a lot of information. And this lot of information is something that we trust and we use for every interaction with the environment. So by developing technology that is used for the cutaneous part, like in this case, we are dealing with an important part of the tactile information flow that stimulates our body to deal with the environment. Well, this is the introductory part, and now I want to go to the application. For sure, you can see here that it was really tremendously difficult to do the multiple contact interaction with this, I would say, cumbersome device, both of them, right? But with our device, it's very simple, with this simple device, to go multiple finger. In fact, as you can see in this application, you see 5 fingers that are working with a virtual environment, and all these 5 devices are applying forces at your fingertips to show at your hand what is going on with the virtual reality. This was impossible before our research because it was too cumbersome the design of the device you were dealing with. I hope that you get this concept. So going highly wearable, dealing with the cutaneous part, because you are stimulating the cutaneous part, you can do multiple contact interaction as never before, okay? This is, for example, a very interesting work where we optimized, the goal of this work is to optimize the rendering algorithm that was specifically designed for our device. So the device design can also inform the rendering algorithms that is important here, because wherever we do haptics, we need to run real time. So all the algorithms should be very, very carefully designed and implemented to be real time. And I tell you that is not easy to do with the current technology. Another important thing, now, I mean, this is the first concept, right? So the first concept, the take-home message is that if you go wearable, you stimulate the cutaneous part of your body, and you can easily design multiple finger interaction paradigms, experiment, and scenario, and whatever you want to do for your research. Another concept here is becoming very interesting, in my opinion, and is something that I talk with my colleagues, with my friend, is what wearability means. So for me, wearability means that whatever you bring on your body does not stop the way your body works. For example, I have this shirt, and this shirt, does not impede any motion in my body. Of course, if this was a cast, because maybe I had a broken bone, it appears wearable, but it's not, because it stops. It impedes the motion of my elbow. Okay, so wearability means that I can move very easily. Okay, but is the only way to think about wearability? Because, for example, in this case, if I have this device at my fingertips, I can move my fingertips, right? But I cannot perceive very easily. So if I go with my fingertip pulp on the desk, I cannot perceive very easily stuff. And this is the reason why we went very highly wearable, again, also for perception, okay? Because we moved the device from the fingertips to the ring level, okay? So we moved from fingertip to ring. This is the ring device. I mean, this will be clear a lot. So the device now is at the ring level, okay? The ring device now let your fingertip free to do the interaction. So you are free, both in motion and in perception. And you can easily type, you can easily move your mouse, and you can easily interact with the environment. Exactly the same application of before, but with the ring type device. Then we can discuss about what does a ring type device means in terms of perception with respect to the fingertip. By the way, the ring is a very important, this is a paper of a few years ago that has been featured also in Science magazine as the first paper that present the wearable augmented reality. Because you can see here in this screen, so I have my fingertip free, right? But I have the rings, okay, that apply forces at your finger. The rings are stretching the skin through cables. So it's not vibration. I'm not talking about vibration. I'm talking about skin stretch, right? Like the platform is moving your skin. Here you have a cable, you have bands that are stretching your skin by applying forces exactly like you are grasping an object. You see here now, the thumb and the index is grasping a box, okay? Then on this box, you put a virtual box, and the virtual box in augmented reality, you can see it, but you can also perceive. So the rings are applying the forces on your body that is generated by the virtual object here. So in some sense, you see, I'm grasping the cylinder, but I'm feeling, thanks to the ring, also the weight of the box on top of it. So we are doing augmented reality in force in this case. Well, so we are doing a lot of experiments. I don't want to go into the details of comparing what it means to do stimulation at the fingertips and stimulation in the ring, but we can, I think, discuss even later on this. Of course, it's not what I want to say is that you see on the right you go for wearability, right? Because you have the typical robot on the left is not wearable. The exoskeleton is wearable, yes and no. The fingertip device is wearable in terms of motor control, so you can move your body. But the ring is perfectly wearable because you can move and you can perceive very easily. The ring you know, in some sense, this is a parallel stuff, because of course what I want to say is that if you are in virtual reality and you are using an Oculus, then it's okay to use a thimble, because then you don't need to interact with the real environment with your hand. But if you have an HoloLens, a Microsoft, so you are in an augmented reality scenario, then you want to feel the force, but also you want to touch real objects. So in my view, the ring device is the perfect companion of augmented reality application, while the thimble device is the perfect companion, is the perfect design for VR application, where you don't need to touch anything else. I think that this is clear, no? If you have questions, just stop me. So this is a design that we made to make a ring a thimble and a thimble a ring and vice versa, you see? So we can have a same design that performs in both configuration. Very well. So we are doing application with ring, with HoloLens. This is a game where we are feeling exactly the interaction at the fingertip tactilely with this is an augmented reality by Microsoft, and we augmented with our fingertips. What we did from this research, we started also a company, and we did a lot of work actually, more. So, and we added, so basically we can, so if you touch, I don't know if you can see myself, but if you touch an object, at the beginning you stretch your skin, right? You have the skin deformation. Then you feel the vibrations coming from the texture, and then you also feel the temperature. You don't feel the temperature actually, you feel the thermal conductance of the device, of the environment that you are touching. By the way, we added in this device, in this thimble device, both the skin stretch, both the vibration, and both the thermal module. And we end up with, you know, here you are touching, deforming the skin, you are feeling with vibration, and here you are feeling the temperature, the conductance of the device. And we are able to render all of them in a very compact device. This was this year in Las Vegas at the CES, where we went to present with the WeArt, the thimble device, showing everything in a virtual environment. In particular, the virtual environment was, you know, a chemical lab showing something. Well, of course, we can do something else. I mean, so the take-home message here is that we have now available, these kind of devices will be available from WeArt next year. And so we are available very nice. WeArt is a company that I co-founded together with a large company in Milano. And now we have a joint lab with 2 PhD students from my lab. And now we have a joint lab between Siena and WeArt. WeArt is between Milano and Siena. Well, we can do something else, okay? We can also use, especially in this part of the life that we are unfortunately experiencing with this isolation. You know, in isolation, there is a lot of problems that refer to the concept of skin hunger. You know, skin hunger means that I want, you know, to touch people. I want to interact with someone else, to shake hands, to touch the shoulder of someone. And this is something that we cannot do, especially if we are isolated because of the COVID, for example, at hospital. And so having this tactile interaction would be really useful. Of course, thanks to our technology, I can handshake now with some of you, thanks to our technology, without being in a real touch. So it's a virtual, it's a remote touch, so without staying close. So what we want to do is to augment the audio and video communication with the haptic communication. This was, you know, a very old application that we did, you see here, very simply, you can touch on one side and you can feel on the other, okay? So you are recording on the left and you are showing on the right. And this is a paradigm of communication, tactile communication, that we implemented like, for example, here, we are imagining a scenario where there was the designer who was at home, and the other one went to China to feel some of the textiles, and one was Guido here was touching different textile, and Chiara was exactly perceiving the textile of the device, of the piece of material, and they were choosing the material. So in some sense, they are sharing the tactile interaction, okay? This is the sense of one of the application that we are imagining to. Of course, we are very active now in e-commerce, and hopefully we will try to do something with Patrizia also in other areas. Well, of course, the emotions are very important, and we are working now a lot on transmitting. We are designing a specific device to transmit emotions remotely, and we want to target exactly this COVID-19 and try to deliver, to transmit, to send the level of emotions that we can decode with tactile interaction. Well, another important application, so tactile interaction now communicate, so to communicate typically emotions or some feature of the device. Another important part of the tactile interaction is the guidance. Yes, is the guidance, and guidance means you have to go right and left. So when humans have to go right and left. So just a second. Here, what I'm saying is that here, for example, in this kind of scenario, we are transforming the way humans interact with each other, because thanks to the tactile channel communication, they can do much more, okay? So this is the first case where I showed from the title of my talk, where this highly wearable tactile device, haptic device, can transform or can introduce new paradigms of communications between humans. Another paradigm of communication is the one that we use for guidance, okay? Guidance is very important. For example, in this case, you have blind subjects, and on the left you see Massimo Vita, who is a very active blind friend here in Siena. I'm sure that Patrizia know him very well. And this is an example where a volunteer in the middle is tactilely guiding two blind, one on the left and one on the right. Okay, with a lot of problems here, yes? Okay, in Siena is not a big problem, but if you are in Milano, for example, this volunteer should go in the place where the blind has the meeting with him, and he has to spend, for 1 hour of volunteering, probably he has to spend 3 hours of moving in the city to reach the place. And also the availability is not very efficient in this way. So what we thought is that, okay, but why don't we, this is also very, a very nice, I want to give you an hint here, because most of the people here were working on instrumented canes, for example, for blind, like putting a belt with radars or other kind of things. So we did something different. And we thought, okay, wait a second. So why we have to develop technology for the blind? Why don't we develop technology for the volunteer? Because it's the volunteer that has a problem now. It's the volunteer that has to spend 3 hours of traveling for 1 hour of a volunteering action with the blind. So the idea is that we have to keep the volunteer at home. So if you want to keep the volunteer at home, basically what you have to do, you have to put a camera on the blind that sends the information flow to the volunteer that is at home. Plus, you have to add the hands of the volunteer, virtual hands of the volunteer, on the body of the blind, like in this case, no? So there is a tactile interaction between the volunteer and the blind, and you have to recover it. So to do this, we used armbands These armbands are like these ones, and these armbands are, they have, in this case, it was very simple vibrotactile interaction, and they were used to inform the subject to go right and go left. I think that the idea is clear. You can see here on the right there is the volunteer that is guiding the blind. Now you see the volunteer wants to let him go on the left. See the index of the right hand of the volunteer. You see now. Moving the finger, the signal reaches the red and it goes on the left. Okay, so we are basically teleguiding, thanks to these highly wearable haptics, a blind around the city. One can say, why don't you use the earphone here, the headphone here, to say to him, go left, go right? Because they don't want to hear anything else but the city, but the environment through the ears. So you don't have to put anything like additional information. This is very important. I mean, this is another application that we did. I mean, we were teleguiding the blind to the pharmacy downtown in Siena. In this case, the volunteer was not at home, was close to him for safety. You know, was the very first experiment that we did implement the Wi-Fi and stuff like that. So, but he was guiding him like if it was at home, and he's bringing the Massimo to the pharmacy. Now he's sending a signal of the orange band, and he turns on left, and he goes to the pharmacy without any kind of audio interaction. So guidance is very important, and also we are using now guidance to do active social distance application. You know that we have to stay far away from each other, and there is technology based on haptics that allow us to stay far away. This is very advanced because this informs the users or where to go to maximize the probability of non-meeting very close someone. And you can see these two guys are optically guided by keeping the distance from each other. They are blindfolded, so they cannot see where they go. Do you see there? They actively, because of the haptics feedback, they are keeping the distance, and they are crossing without meeting, without having less than 1 meter distance. Okay, so we are using this also for social distance. Another application that I recently patented and was published on IEEE Transaction Haptics. I don't know if you know IEEE Transaction Haptics. I want to talk about it because I'm the editor-in-chief of this journal, and it collects a lot of, I mean, all the contribution on haptics. So if you now or in the future you have a contribution on haptics, we are very happy to welcome you in our journal. By the way, so we published this work here, and this work is on social jogging. It's still about the guidance, but it's guidance in terms of the cadence, the rate of your running. So the idea here is very simple. So I want to okay, so I have these anklets, okay, exactly the same technology of before. The anklets here has an accelerometer. As soon as the accelerometer touches, I mean, as soon as the foot touches the floor, the accelerometer registers an information, like in this case. And when there are these peaks, okay, these peaks are sent on the friend that is somewhere else. Is in Milano, the other one is in Siena. Okay, so as soon as the girl in Siena touches the floor, generates an impact that is recorded by the accelerometer and is sent to the leg of the friend in Milano. So the friend in Milano feels on the leg the haptic feedback, the vibration of the impact to the floor of the lady in Siena. So she's feeling on her legs the cadence, the running step of the friend, and vice versa. Okay, in a scenario like this. This is the application I want to. Now they are chatting each other. They say, please connect. And so we go for running together. So it's a sort of augmentation of like Runtastic or Nike application by tactile feedback. And they start to run. She's sending the signal. And now, I mean, actually, this was at the same, this was a little bit before, no? they were talking each other. And now she goes to run and with the anklets, and while running, they are feeling exactly each other on the right and on the left. I mean, they are connected, okay? When they are connected, what happens is that basically we, for example, if myself and someone of you starts to run in different place and we are connected thanks to this technology, it happens that then we go to the same cadence. So we synchronize, okay? So my step goes to the same velocity of the step of someone of you. So maybe you can be my physiotherapist, and so you can give me exercises like augmenting the step. You know, we can invent many paradigms in terms of communication. So this is another example of how this highly wearable technology can create new paradigms of interaction. So for guidance. We applied also this technology for Parkinson, and you see here on the left, there was a Parkinson subject with very short steps. You see, very short steps on the left, with the anklets are turned off. When you turn on the anklets, you see how the steps becomes regular, okay? So these, you know, we are finding many applications also with the freezing. I mean, I don't want to go into this detail, but we are finding many applications also in rehabilitation and in Parkinson disease. We recently published on neurological science a paper showing this kind of application. Well, because one of the paradigms that we are using in my lab is that we are using at the initial of our research, we are using always medical motivation. So we are helping people, okay? And as soon as we help people, then we start thinking about applications that are for healthy subject. For example, this is for Parkinson, this is for jogging. I mean, it's for healthy subject, because I think that if we develop technology not only for people with impairments, but also for healthy subject, this will be an improvement, a plus also for people with impairments, okay? For example, you have a lot of devices more, the cost goes down, the research is more, is richer in terms of arguments, and you have more scientists doing it. So in my opinion, I think that we need, as scientists, we need always to couple the applications for people with impairments with application for healthy. I don't think that is, I mean, in my lab, we don't consider a good strategy to work only in for people with impairments or only for people that are healthy. Well, another important aspect that I want to talk now is the interaction with the machines. And I will present something that I really love. I will take 6-7 minutes to show it, and then we go to the talks. Sorry, to the question time. Well, the application is very simple here. But is as simple as interesting in my view, because you see here there is this subject, for example, that got a stroke, Alessandro, and is not able to grasp the bottle anymore, right, with the right hand. And of course, you know, in this kind of case, is not able to, you know, to open the bottle, to do bimanual manipulation anymore because of the stroke. In this case, was really strange. I didn't find any technology for this kind of subjects, because, you know, most of the people were working on amputee, with people that are lost their hands. And but amputee is not, so the number of, so for me, for example, in, I don't know, in 30 years, it's more likely that I will be in a situation like this for a stroke than in a situation like maybe even 40 or 50, maybe. Then in a situation that I'm losing my hand, because I mean, it's very unlikely that I will lose my hand like an amputee. It's more likely that when I will be very old, that I will have a stroke. So what I want to say is that the population of people having this disease is much higher, is much larger than the population of people that are amputee. So there was no solution. I mean, a lot of prosthesis, like I told you. So by looking how the hand work, so we simply got a very simple idea. So we said, why don't we use the residual part? I mean, what you need to grasp an object? To grasp an object, you need a palm, basically, and a thumb, okay? So what about using the residual part of the hand like a palm of Alessandro, and just adding an additional finger? So we added an additional finger here, okay? This additional finger is making an hybrid grasp between the human and the body, and we invented this sixth finger. This sixth finger is this one. Now it adapts to any kind of object. You start seeing the wearable on the left. I will talk in a moment on the wearable haptics on the left. This is very important here. It's a way of interacting. Now I have a very nice interaction between a human and a machine, that there is a sixth finger, and I want to augment this interaction by wearable haptics. You know, they are able to do this kind of things. They are asking us to design this device that are waterproof, because they are working with, of course, water in the toilet or in the kitchen and whatever. You are able to, you know, to grasp again object, and you're able to move your hand again. So sorry, not the hand, the arm. So there is a reason to move the arm. If he does not have the additional thumb, he does not move the arm at all, because you don't move the arm if you don't have the hand. Okay. This device is wearable. We are quite obsessed by wearability, and we designed it to be wearable. And this is how to interface this. This is very interesting. I will show you this stuff. This subject, because of the stroke, okay, is able to move the arm, but has no perception here. So he has no feeling of anything. It's like a piece of wood in terms of perception. This means that he does not recognize the time where there is enough force between the robot and the hand squeezing the glass to move the glass up. Luckily enough, thanks to our wearable haptics device, we can recover the haptic feedback on the contralateral part. The right hand is able to perceive. So we simply connected the haptic feedback on the ring that we were designing before to the signal coming here. So here there is a force sensor. As soon as the force sensor tells, yes, there is enough force to lift the glass, we send an haptic feedback, a tactile feedback on the contralateral hand. So we are, in practice, we are augmenting the perception of the subject by using our wearable haptics. So he is able to recover the perception of something that is not able to perceive anything by our technology. You see here, now he's squeezing with the finger. He does not perceive anything, okay, neither visually, because this is rigid. As soon as there is enough force, vibration occurs here, he understands that he can lift, and he lifts the object, okay? So this highly wearable haptics is a new way to let the robot communicate with the human for a very fluent and interface intelligent communication between the human and robot. So in practice, we are using this kind of paradigm thanks to our wearable interface in the middle that recognize, I mean, when I say, so in the middle, there is the ring, right? When I say feedback in the bottom of the middle box, I say the haptic feedback that goes from the sensing of the robot to the perception of the human. The action here, you see on the ring, there is a button. The button is switched by the thumb, the healthy thumb, and as soon as the subject switches the thumb, the robot starts. So the action of switching the switch is recognized, and the actuation of the robot starts. So we are basically sensory motor interfacing the human with the robot. Just a last. So this is, I mean, I want to just to show this video, and then we go to the question. So the video here is a video by we did with Alessandro on his sailing boat. He was not able to control anymore because of the stroke. Now, thanks to the extra finger, he is able to control and to sail with his boats again. It's just 1 minute video. Stay with me, and we'll be back in a second.
Io sono Alessandro Bondi, ho 52 anni e ho avuto 4 anni fa un ictus. Ho sofferto per molto tempo, ho visto un barlume di speranza nella tecnologia che mi ha portato a sperare di tornare sulla barca a vela. Mi sono avvicinato all'equipe di Domenico, Prattichizzo, che è l'ingegnere che ha inventato il sesto dito.
Nel caso di Alessandro è estremamente utile perché creerà una presa di tipo ibrido, una presa fatta dall'uomo e dal robot. Consiste in 3 parti principali: un motore che attraverso dei tendini trasmette il movimento a questa parte rigida e flessibile che consente di afferrare degli oggetti adattandosi a qualunque forma.
Mi rende in qualche modo un cyborg.
I started collaborating with Alessandro since many years, and now we know each other by work, and now we are very, very friends. We also have now a startup on this sixth finger that was started by Enovia, and this sixth finger is becoming, a product. And this is the new design. This is the ring. This is the device on the left. I was in Las Vegas showing the application of the extra finger. in this case, very nice engineered, but with the same principle of before. And we are also focusing on the wearability. For example, here in this video, you can see how easy it is to wear and to use the extra finger, assuming that you have apparetic hand. Okay, and this is the latest design of the extra finger by the company Existo, and also this one has a concept that is the concept of being wearable, because this becomes rotates and wraps around the arm and stays under the jacket. Okay, so I showed, this is the conclusion, I showed how from the state of the art, that is the grounded device and the exoskeleton, we went to thimble device, to ring device, to armband, and we showed different paradigms of communication that goes from Parkinson, social jogging, human-human emotional interaction, till the end of augmenting the sensory motor abilities of a human who lost some of their abilities. So we are talking about augmentation. These are some of my publications. You can also look for the current 8 patents that we submitted in the last 3 years on this subject. And this is a current last book that I wrote on augmentation, where there is an interesting part on the sensory motor interfaces. So thanks for your attention, and I'm ready for your question, in case there are.
Thank you very much, Domenico. There are, yes, already many questions on the chat, so I will maybe let Vikram start with the question. Please, Vikram.
Yeah, thank you, Domenico, for a very nice presentation. So my question is about, in the beginning, when you were talking about the fingertip cutaneous thing for the VR application. So I was wondering that why have you considered using air pressure for haptic effect, like mid-air haptics can put the pressure points on the fingertips, something like that?
Yeah, we are. I mean, we know very well the friends from that are doing the air pressure stuff. They recently, I think, changed the name of the company, but I mean, this kind of air pressure is very interesting in my opinion. Okay, but still has the limits of being like grounded. So you have to have this air pressure pad, and you put your hands on top of it to feel it, right? So you have to stay in this environment. Okay. So what we are trying to do with our highly wearable stuff is to avoid staying in a closed workspace. So we distinguish between grounded device and wearable device. So grounded means that you have to stay in a workspace. like a robot. Now, the mid-air device still suffer the problem of being like grounded, because you have to have the device, the air, pressure mid-air device on a desk, and you have to put the end on it. You cannot go walking in Milan or Siena with those kinds of devices. It can be nice to combine both of them, but no, we are not doing. In there, we are doing something now that is called very recently soft haptics. So we are working now with something that is like using high pressure to have some balloon that you the size of, and you can have some, but still mechanical interaction with it.
Okay, thank you. So if I may just ask one small question, one more. So how do you simulate the texture of the objects? Do you do that, or it's purely the haptic effect or vibration?
No, we are simulating. So the device that we are using for vibration is a piezoelectric motor with a proprietary controller for it, and we are able to do very high fidelity interaction. Just to give you an example, I have this shirt, okay, and this tie, so we are able to perceive the difference between these. I mean, you can see here there is some texture here.
Yeah.
You're able to perceive the difference, okay?
Thank you.
From shirt, it's not easy to perceive the difference from similar shirt,
Okay.
but shirt and ties. For example, if you take a shoe, like sneakers, okay? Those kind of sneakers are done by different materials, right? Then with our technology, you can perceive exactly the different materials. So if you have the same object done with different texture, it's perfect.
Great, thank you.
Sure.
So maybe now, Ank, you also had
Yeah.
Ank, the first.
I think that was me first.
Oh, yeah.
Yeah, thank you, Domenico. I found your talk very, very interesting. So I have been working also a little bit with haptics and blind people and helping people. So I really like this motivation. I was wondering if you're also looking at not only if your haptic prototypes work, but also how people appreciate them. Like, for instance, in the 6 finger, do you have any feedback on satisfaction or user experience and things like this?
So you are touching a very important point, because the background of my lab is engineering robotics technology. And of course, especially in a very interdisciplinary arguments like this one, we had to bring in our lab the knowledge that is needed to do this kind of study. So we became expert in terms of using it, of course, the state-of-the-art methods in user studies, especially in measuring like JND or comparing performance in terms of time of execution of tasks and things like that. Very recently, we are collaborating with groups that do also satisfactory studies, evaluation with qualitative test that we are doing. We are not expert of this test. This is also one of the reasons why we are very happy of collaborating with people, and we collaborate with people for this. And from those kind of evaluation, we understood, for example, a lot of things like that. For example, we went to the sides of the finger. People were very happy with the finger, but they liked to have a smaller size, closer to the thumb, to the real thumb size. And through this evaluation, we went through new round of design and implementation. So yes, we are doing, but as in terms of scientists, as users of state-of-the-art technology and knowledge, and more interestingly, by collaborating with groups. Thank you.
So, Ank?
Thank you. And thank you for the talk. It was very interesting. I have a question about the design decision for doing like the armbands, doing it left and right for guiding blinds, because you just have this sharp left and right and nothing really in between, because I know there also works for guiding blinds using kind of a belt. So why did you use just the arms basically? For the steps I see it, but for the guiding.
We used it because of simplicity. No, we did a lot of studies in this sense. For example, we measured how many kind of before going into this final design. We tested, for example, a single armband with a different tactile pattern that, like, going, for example, this pattern go left, or this pattern go right, or this pattern go straight, right? So many, like on the armband, on the belt, and blah, blah, blah. But at the very end, the simpler, the better. So because in any case, you have still to learn some new language that is your haptic language. And even, for example, right now, the smartwatch here, you can have the haptic feedback that tells you if you want to go left or right in the car, okay, when you use Google Maps. Okay, but still I'm not able to distinguish. So it reads a more cognitive load to understand what is meaning for. If I have two smartwatch, one for the left and one for the right, I will go left snap.
Okay.
And this was, for example, what was Anke saying. Both of you is Anke name.
Yeah.
Okay. Said that through this evaluation and the way that people like the interface, we went through the simpler, the better principle of design.
Okay, thank you.
Thank you.
There is one question from Mira as well. Please, Mira.
Hello. It's a very interesting presentation. I have a question concerning connecting people with the wearable when they were jogging, one from Siena and the other in, this slide when you showed it. And I was thinking about also, what about if it to transmit emotions from one friend to another on a long distance, especially that people are now living far, and then when someone is talking with someone on the phone and he is stating a problem or something, how the other can feel the feelings with this wearable. Is it what do you think about it actually?
So I think that so there is one thing that is very important. So if I feel, for example, if I feel that you are handshaking me now with the device while touching, because I'm used now. Suppose that we have some device now, and now while you give me the question, suppose that you are handshaking me with some device. Okay.
Okay.
Okay. Now in this case, so my perception. Sorry, not my perception is that you are here, because if you touch me, in some sense you enter in my peripersonal sphere. So you are to stay really close to me to touch. So I am used to this a priori. Okay. So if someone touches me, is very close. So the fact that I feel your hand on my hand through the device, of course, is like giving me the impression that you are very close, and brings us to a different level of communication, because you are here. No, there is a closer communication. So one is so we immediately deliver, in my opinion. When I say in my opinion, is that because it's some research that we are doing right now, is the proximity concept. So as soon as there is a tactile communication, it means that she is here. Okay, so this is the first concept. The second concept is that something related more to emotions. For example, we were doing this kind of test where we were simulating the aspect where there is two sisters, for example. Okay, one is pregnant, the other one no, and the one, I mean, she's touching the bell, and while the sister is feeling exactly what she's touching, and eventually she was also feeling the heartbeat of the baby inside. So this kind of course, the emotion that we deliver from one side to another should be very full of meanings, no? It's not, you have to, there should be a context around this stuff. What we believe is that adding this level of tactile communication will dramatically improve the emotions that you can transmit from one side to another. Now, what we are doing, I mean, this is right now we are designing the device. We did not any experiment yet, but just pilot to see the concept of the experiment. And what we are doing is to do in the quantitative measurement of the emotions through tests and things like that. And also we are studying the physiology of the humans to understand what is the right design of the wearable haptic, wearable tactile stuff to deliver this kind of information. So on one side, we are studying how to measure the emotions with the tests. On another side, we are studying the physiology of the emotions. For example, just to give you an example, maybe it's better to put the device on the forearm than the fingertip for the tactile interaction. And this is because maybe here there are receptors or fibers that are closer to the emotion way of processing the brain do.
I have just a small comment. Do you have like a publication already about how to measure quantitatively emotions?
No, there are publications, but not from us. So there is a literature. I mean, Patrizia is saying yes. So there are is the literature that we are studying to make it working.
Okay. Thank you.
Sure.
Patrizia, you also had a question. We are running a little bit late, so maybe short, very short. Can I stress?
Okay, so first of all, thank you, Domenico, because your talk demonstrated that dreams can come true. And I think this is really an excellent example of how the research can mature in time, and then the outcomes can go to the market with these startups and patents. So I really appreciate your excursus and your milestones. I have a question, is very philosophical. One of my concern with wearables is that in some cases they are somehow colonizing our body. And when technology comes very close to the body, a lot of questions arise, like aesthetics, for example, ergonomics, but more in terms of what is emotional. You know that I work a lot with people with disability. When I worked with deaf people, for example, they complained about the stigma of this kind of prosthetic solutions. And so I was wondering if you had the same problem, or if you heard about the people you work with about this idea of reducing the stigma of this kind of systems that, as I said, try to colonize our body rather than, evolve in a more harmonic way with the body of people that is a cultural body. So we have to think about a lot of issues when designing wearables.
Yes, Patrizia, thanks for this question. This is something that so the first answer is this one. So when we designed the extra finger to be like a sort of bracelet, no, wrap around the wrist and goes under the jacket, is exactly in this direction. So by reducing the stigma, so basically you have a bracelet, and then this bracelet becomes an extra finger only when it's needed. Okay. The other thing is that, well, I will never, if I see the hands of you, is impossible to see any one of you with the thimbles, but maybe rings, yes. So the ring per se can be a design, a concept, form factor that is more, used to have on our body. So it colonizes, but in a sustainable way, in some sense. And on the other side, I think that, so I have something that I'm studying now, even maybe even publishing, because I mean, for example, now if I see something that I don't want to see in the screen, I simply close my eyes. No, I have the palpebra that stops the flow. But if you put something on my body, there is no palpebra, right? So there is no way to stop the tactile information in my body. So I think that tactile is more intimate because there is, you know, if I don't want to see, I close my eyes, I put my head. If I don't want to hear, I put something like this. But if you have something on my body, either you simply take your device and you move it away, but there is no natural way to stop the tactile communication on your body. So in some sense, I think that is a little bit more. So when you say colonize, I think that we have to be careful because the tactile information, we don't have any direct defense to stop the tactile information on our body. And we have to be careful. So I think that the app for tactile interaction should have a sort of a stop button because I don't want to feel what you are sending me anymore. No, so there should be a sort of palpebra-like in the interface. In terms of what you are saying, the aesthetics is really for me challenging. I am not an expert, but I like a lot to think about it. And now I really don't remember the name, but you certainly know. She's doing a very fashion design, the prosthesis for the legs, even dresses with Anouk. I don't remember the name of the scientist. So she's in some sense exaggerating and making the prosthesis even as less bio-inspired as possible. For example, there was a prosthesis like a cone with a point of contact on the floor. I don't know if you ever see it. By the way, I think that instead, maybe in the future, I don't know, if we get used with this device, instead of trying to hide or just to make it more harmonic, maybe we have to find a new language to make the device for disability a fashion object per se, as different as possible with respect to the rest. But I'm not an expert. I think that is a big problem, and I would like to know what's going on, even to design our, because it's also informing us, because the way we put the motors and the sensors in some sense defines the future possible shapes and aesthetics of the device. So by having some principle is important for us as well that are technologists.